I'm going back because I only have 1 hit point and I don't want to die all the way over there.
Okay.
So what I'm going to do is I'm going to explore near where the bench is so that if I die, I don't have to go very far. There's 2 types of search in computer science: depth first search and breadth first search. Depth first search is you go all the way down a path and find a dead end before you turn around and go back. Breadth first search is you first explore all the junctions that are near your starting point, then all the junctions that are 2 away from your starting point, and so on. So in breadth first search, I would go here and I say, oh, I can go up or down, so let's go up. And I get here, and then, oh, this is another junction, but it's 2 away. Like, this is 1 away from the starting point. So before exploring that, I'm going to go down here and check this first. And then once I've explored all the junctions that are 1 away, now I explore all the junctions that are 2 away. So I can go to this guy, go, let's say here, oh, that's another junction that's 3 away. So let me look here first. This is also 3 away. So now I can do either of these. And then I'll explore this, and then here's 4 away. So before I explore that, let me explore the one that's 3 away, and so on. And it's
What are the...
yeah, it's very inefficient because you have to backtrack a lot.
Yeah.
But in the case of this game like this, it's more likely that you'll find all the secrets if you do breadth first search.
I see.
With depth first search, you might make progress, like you fight a boss or something and you go somewhere, and then you can't go back anymore.
Right.
It's like the whole Metroidvania stereotype of this is the right way, so let's go the wrong way first to make sure we find everything.
I was thinking that that way also mimics what most people would actually do in real life. Like when you go and visit a new city or you're going on walks in your neighborhood or something, you can only travel so far. And so you do
Oh
a
my
lot
gosh.
of...
I lost my money. Gosh darn, I died twice.
You end up doing a lot of short trips in every direction. Why are there names for those 2 different types of searches? Why would that be so...
I mean, there's names because it's useful to refer to them specifically.
Yeah, tell me a little bit about that context.
Well, I mean, like, there's 2 things, right? There's 2 obvious ways of doing it. Those were the 2 obvious ways of doing it. Maybe that's your question. Why were those the 2 obvious ways?
I guess, what are you searching for?
Oops.
Is it just related to video games?
No, it's a data structure thing in computer science. But give me
Yeah.
a second because we're being raided by Zenith. Zenith, thank you so much for the raid. You were playing Claire Obscure. How was that? How did it go? Raiding and running. Have a good stream. All right, Zenith. See you later. Enjoy Silksong. Thank you. What was I saying? There's data structure,
architecture?
data structures. Yeah. So a common
Okay.
data structure is a tree, which is like a graph, which is when computer scientists or mathematicians talk about graph, they're talking about points and nodes. They're not talking about a line chart. So layperson, when they think of graph, they think about something like this, right? Like a chart. That's usually not what mathematicians or computer science talk about. They're talking about like you have a node and lines. So a very common data structure in computer science is called a binary tree, which is like this, where you have a root node and then it has child nodes, each of which is itself recursively a binary tree. So you have the node and you have the left subtree and the right subtree.
Okay.
And then there are various operations you might want to do on the tree. For example, if each node has a number associated with it, a value, maybe this has 3, then this has 5, and this has 7 or whatever, you might say, so what's the sum of all the nodes in the tree? So you have to visit every node in the tree to do that.
Okay.
And so there's 2 obvious ways of doing that. You start here, and you go all the way down to the left. When you reach it, then you come back, and you look at this guy on the right. Then you come back, and now you've looked at both of these guys. So now you go here, and then now this guy says, well, I finished my left, so now I'm going to do my right. This guy says, well, I haven't started my left, and yeah, so I'm going to do that. And so this order is called depth first order, or depth first traversal.
What word are you saying? What first?
Depth. D-E-P-T-H.
Depth. Thank you.
And then the other is breadth.
Gotcha.
Is there an A in breadth? I don't remember.
There is, yeah.
Okay. So like this, but spelled correctly.
Right.
And that's saying you look at
Perfect.
this guy first, then you look at these 2 guys, then you look at these guys, and then these guys, right? So the idea is you look here, you go here, and then before going to the guy that's 2 distances away from the root, you look at this guy because he's only 1 distance away from the root.
Right.
And then,
So almost by levels.
yeah. But if there's a cost to quote unquote move, like if you're here and it takes energy to go here, then you got to go back and then go here, and then it takes energy to go back again. That's what makes breadth more inefficient. But if you don't have to move, if you're looking at from above and you're just saying, I'm going to look at this and look at this, then it's not as apparent why breadth is less efficient than depth.
What is an application of this? Why would there be a cost associated with it?
Usually in terms of implementation, the cost is keeping track. It's a memory cost.
Okay.
Because you can't see the entire tree at once as a computer program. You only have access to a pointer to one location in memory.
Okay.
So you have a pointer to this object, this node, and then it itself has a left pointer and a right pointer. So it's getting very technical. There's something called a stack, which is an easy way to store information. So what you can do is you can push the address of this memory on stack. I don't know how to represent that visually. But then if previously your stack pointer was here, now your stack is here at the empty spot, and you can go down and do stuff. And then you're doing a recursive subroutine. So the idea is when you're writing an algorithm to sum up all the numbers in the tree, you say the function of summing up all the numbers in a tree is you take the value of the current node, cur for current node, plus you sum up the left tree, plus you sum up the right tree.
Okay.
And so the idea is instead of giving instructions like go left and go left and go left, I create a definition that recursively refers to itself. To sum a tree, its current plus the sum of the left subtree and the sum of the right subtree. In the same way that for the Fibonacci sequence, you can define it as to find the 7th Fibonacci number, all you have to do is find the 6th Fibonacci number and the 5th Fibonacci number and add them together.
Okay. Given that breadth-based searching has more of a cost, what is the reason why you might use it? A non-video game reason.
I have trouble coming up with an example.
Would it be helpful if you're more likely to encounter the information on a shallower level?
Yeah, I guess so. So if you have some reason to suspect that the information you're looking for is high, then yeah, I guess you would want to use breadth, assuming you can tolerate the additional memory costs. I think most computer scientists just reach your depth as their default choice if they don't care, because it's known to be more efficient that way, memory efficient.